Hello and welcome to Math Zone African Motives. In this tutorial, we will be diving into a very important and powerful integration technique. We're going to explore the method of integration by parts. This method is essential for solving a specific type of integral, and by the end of this video, you will be able to, first, derive the formula for integration by parts from the product rule of differentiation. Second, apply this formula correctly to solve various integrals, which often involves using a helpful mnemonic called ILATE. And third, you will be able to recognize and solve the integrals that require integration by parts, including those with special recursive and cancellation properties. Let's get started with the foundation of this method. Before we get to integration by parts, let's briefly recall another common integration technique. Sometimes you'll encounter an integral where the integrand is a product of a function and its derivative. The formula for this is the power rule for integration applied to a function. It states that the integral of f of x to the power of n times its derivative f prime of x is simply f of x to the power of n plus 1 all over n plus 1 plus a constant of integration. This rule works great when you can identify a function and its derivative within the integral. For example, consider the integral of x squared plus 1 to the power of 3 times 2x. Here, if we let our function f of x be x squared plus 1, its derivative f prime of x is exactly 2x. So this integral fits the pattern perfectly. We can solve it by taking our function f of x, which is x squared plus 1, increasing its power by 1 from 3 to 4, and dividing by that new power. The answer is x squared plus 1 to the power of 4, all divided by 4 plus c. Simple, right? But what happens when the product in our integral isn't a function times its derivative? This is where integration by parts comes to the rescue. So, we've identified the need for a new method. Our objective in this scene is to derive the formula for integration by parts. We will derive the formula for integration by parts. This method is based on a rule from differential calculus you should be familiar with: the product rule. Let's start with the product rule for differentiation, which tells us how to differentiate the product of two functions, say f of x and g of x. The derivative of f times g is equal to the derivative of f times g plus f times the derivative of g. Now we can integrate both sides of this equation with respect to x. Remember, the integral is the antiderivative. So we have the integral of the derivative of f of x times g of x equals the integral of the derivative of f of x times g of x plus the integral of f of x times the derivative of g of x. The integral of a sum is the sum of the integrals. So we can split the right side into two separate integrals. On the left side, the integral of the derivative of f times g is just f times g itself. This is because integration and differentiation are inverse operations. Now, let's rearrange this equation. We'll subtract the first integral on the right side from both sides. And this, right here, is the core formula for integration by parts. It's often easier to remember this formula using the alternative notation with u and v. Let's define a new set of variables. We'll let f of x be equal to u, and we'll let g prime of x dx be equal to dv. So we are making the substitutions u equals f of x and dv equals g prime of x dd. If u is f of x, then the differential do is equal to the derivative of f of x, f prime of x times dx. And if dv is g prime of x dx, then to find v, we just integrate dv, which gives us v equals g of f. Now we substitute these into our formula. The integral of f of x g prime of x dx becomes the integral of u dv. On the right side, f of xg of x becomes uv, and the integral of f prime of xg of x dx becomes the integral of v do. This alternative notation, the integral of u dv equals uv minus the integral of v du, is the most commonly used and remembered form of the integration by parts formula. We have successfully derived it from the product rule. Now that we have the formula, the big question is, how do we apply it? Our objective in this scene is to learn how to apply the formula. We're going to learn how to apply the integration by parts formula using a rule to choose u and dv. Remember our formula, the integral of u dv equals uv minus the integral of v du. The key to making this method work is to make a smart choice for which part of your integrand will be u and which part will be dv. The goal is to make the new integral, the integral of VDU, easier to solve than the original integral. To help us with this choice, we use a mnemonic device. ILATE. ILATE stands for a hierarchy of function types. It tells you which part of your integral to choose as U. I stands for inverse trigonometric functions, like arcsin or arctan. L stands for logarithmic functions, such as ln of x. A stands for algebraic functions, like x squared or the square root of x. T stands for trigonometric functions, like sin or cos. And E stands for exponential functions, such as e to the x. The rule is simple. When you have a product of two different function types, you choose U to be the function that comes first in the ILATE list. Let's put this into practice. Here's the procedure, or the 3 steps, for finding an integral using integration by parts. First, we'll choose U and dv according to the ILATE rule. Second, we need to find the differential do by differentiating U, and the function v by integrating dv. Third, we plug these 4 parts, u, v, dt, and dv, into our formula and solve. There are a few key things to remember. This method is usually longer than simpler ones, so you only use it when necessary. Also, if your integral doesn't look like a product, you can often treat it as 1 by setting dv equals to 1. We'll see this in an example. You may also need to apply the method more than once, and sometimes you'll even get the original integral back, leading to a clever recursive solution. So, to recap, we use the ILATE rule to choose u and dv. We differentiate u to find do and integrate dv to find v, and then substitute them into the formula. This is the heart of the technique. All right, let's start with our first example. This will help us see the ILATE rule in action. Our objective here is to evaluate the integral of x times the natural logarithm of x. Let's look at our integrand. We have a polynomial function x and a logarithmic function, ln of x. Now, let's use the ILATE rule. I is for inverse trig, L is for logarithmic, A is for algebraic. Logarithmic comes before algebraic in the list. This tells us to set our u to be the logarithmic part, so we'll choose u equals ln of x. Consequently, the remaining part of the integral x dx must be our dv. Now for step 2 of our procedure. We need to find do and v. To find do, we differentiate u. The derivative of ln of x is 1 over x, so do equals 1 over x dx. To find v, we integrate dv. The integral of x dx is x squared over 2 plus a constant. We can ignore the constant here because we'll get a general constant c at the end. We have all 4 parts, uv, do, and dv. Now for step 3, apply the formula. The formula is the integral of u dv equals uv minus the integral of v dt. Let's substitute our parts. First is uv, which is ln of x times x squared over 2. Then we subtract the integral of v du, which is x squared over 2 times 1 over xd. Take a look at that new integral. It's the integral of x over 2. That's much simpler than our original integral. This confirms our choice for u and dv was a good one. Let's simplify. X squared over x is x. We can pull the 1/2 out of the integral. The integral of x is x squared over 2. Finally, we multiply and add our constant c. This gives us our final answer. X squared over 2 times ln of x minus x squared over 4 plus c. Let's verify this with the provided memo. The memo gives the same result, confirming our calculation. Verified using memo. For our next example, we have a product of an algebraic and a trigonometric function. Let's determine the integral of x times cos of x dx. Again, we start with the ILATE mnemonic to choose our u. We have an algebraic function, x, and a trigonometric function, cos of x. A comes before t in ILATE, so we set u equal to x. So u equals x, and the rest, cos of x dx, is dv. Next, we find do and v. The derivative of u equals x is simply do equals dx. The integral of dv equals cos of x dx is v equals sin of x. Now we apply the integration by parts formula. Integral of u dv equals uv minus the integral of v du. Substituting our parts, we get x times sin of x minus the integral of sin of x dx. The integral of sin of x is a basic integral we know. It's negative cos of x. So we have x sin of x minus the integral of sin of x, which is negative cos of x. Remember to add the constant of integration, c. Simplifying a negative times a negative is a positive. So our final answer is x sin of x plus cos of x plus c. Let's check with the memo. The memo confirms our result. Verified using memo. Our third example presents another case of an algebraic and trigonometric product. Let's evaluate the integral of x times secant squared of x dE. Again, using ILATE, algebraic x comes before trigonometric secant squared of x. So we set u equal to x and dv equal to secant squared of x dx. The derivative of u equals x is do equals dx. The integral of secant squared of x is tangent of x. So v equals tan of x. Now we apply the integration by parts formula. Substituting u, v, and do, we get x times tangent of x minus the integral of tangent of x dx. The integral of tangent of x is a standard result. It is the natural logarithm of the absolute value of secant of x. So we have x tangent of x minus the integral of tangent of x, which gives us minus the natural logarithm of the absolute value of secant of x. Don't forget the constant c. Our final answer is x tangent of x minus the natural logarithm of the absolute value of secant of x plus c. Let's check with the memo. The memo matches our result. Verified using memo. This next example is special because it doesn't immediately look like a product of two functions. Our objective is to learn how to integrate functions that don't seem to be products. How do we find the integral of just the natural logarithm of x? The trick here is to consider the number 1 as a separate function. We can write ln x as 1 times ln x. We rewrite the integral as the integral of 1 times ln of x dx. Now it's a product, an algebraic function, 1, and a logarithmic function, ln at. According to ILATE, logarithmic comes before algebraic. So we set u equals ln of x and dv equals 1 dx. Differentiating u, we get du equals 1 over x dx. Integrating dv, the integral of 1 is x, so v equals x. Now let's plug these into our formula. uv minus the integral of v du. We get ln of x times x minus the integral of x times 1 over x dx. Take a moment to look at the new integral. It's the integral of x over x, which simplifies to just 1. This is a very easy integral to solve. The integral of 1 is x, so our expression becomes x ln of x minus x. Finally, we add our constant of integration, c. Our final answer is x times ln of x minus x plus c. The memo confirms our result. Verified using memo. Our fifth example in this set is a bit of a trick question, designed to see if you can recognize a simpler method. The question is to find the integral of ln of x divided by x. Let's start by trying to use integration by parts, as we have been doing. We can rewrite the integral as ln of x times 1 over x. Using ILATE, we set u equals ln of x and dv equals 1 over x dx. This gives us do equals 1 over x dx and v equals ln of x. Applying the formula, we get ln squared of x minus the integral of 1 over x times ln of x dx. Notice what happened. The integral on the right is the same as the integral we started with. Let's call the original integral I. So we have the equation I equals ln squared of x minus I. We can now solve for I. Add I to both sides to get 2I equals ln squared of x. Then divide by 2 to get I equals 1/2 ln squared of x. We add the constant c to get the final answer. Let's verify this result with the memo. The answer matches. Now for the important lesson. While integration by parts worked, there was a much simpler way. It was hiding in plain sight. Let's look at the alternative solution provided. Recall the power rule for functions. The integrand len x r x is actually the natural logarithm of x, which is our fx, times its derivative, 1x, which is fx. This is a perfect candidate for the substitution method. Let u equals ln of x. Then do is 1 over x d. Substituting these into the integral gives us the integral of u do, which is 1/2 u squared. Plugging back our expression for u, we get 1/2 ln squared of x. Adding c gives the exact same result. As you can see, the alternative method was much faster. This highlights a crucial point. Always check for simpler integration techniques like substitution before jumping to integration by parts. Integration by parts is a powerful tool, but it's often more complex, so we use it when other methods fail. Our next example introduces a new technique. Our objective is to learn how to solve integrals that recur. We need to find the integral of e to the power of 2x times cos of 2x dx. Here we have a product of an exponential function and a trigonometric function. When using ILATE for e and t, it can be a bit tricky, but a common practice for these types of recurring integrals is to choose it to be the trigonometric part. So we'll set u equals cos of 2x and dv equals e to the 2x dx. Differentiating u gives do equals 2 times sin of 2x dE. Integrating dv gives v equals e to the 2x over 2. Plugging into our formula, we get e to the 2x over 2 times cos of 2x plus the integral of e to the 2x times sin of 2x dx. Notice the two negative signs canceled out. We have a new integral e2x sin to 2x dx. This integral is similar to our original one. This is a sign that we need to apply integration by parts again. We will apply integration by parts to this new integral. It's important to be consistent. If you chose the trig function as u the first time, do it again. So we let u equals sin of 2x and dv equals e to the 2x dx. This gives us do equals 2 cos of 2x dx and v equals e to the 2x over 2. Applying the formula to this part, we get e to the 2x over 2 times sin of 2x minus the integral of e to the 2x cos of 2x dx. Now we substitute this back into our main equation. Original e key, e2 b ct casca 2x dx equals e2 as isax 2 rt is 2 as isaca plus e2 as c that ct dt substitute e2x equals p2 e dt e2x2 dt 2x p e2x stiget t e2x key 2 is d. And look at that! The integral on the right is exactly the same as the integral we started with on the left. Let's call our original integral I again. The equation is I equals e to the 2x over 2 times cos of 2a plus e to the 2x over 2 times sin of 2x minus I. To solve for I, we move the I to the left side by adding it, giving us 2I. Then we divide by 2. Finally, we multiply through by 1/2 and add our constant c. This gives the final answer. The memo confirms our answer, verified using memo. So for these recurring integrals, you apply integration by parts twice. Then you treat the integral itself as a variable in an equation to solve for it. It's a very clever technique. Our next example involves a trigonometric function to a power. Our objective is to learn another way to handle integrals of powers of trigonometric functions. Let's find the integral of sine squared of x. This one is interesting. We could use a half-angle identity, but the problem explicitly asks to use integration by parts. This shows you how versatile the method can be. We'll write sine squared of x as sin x times sin x, making it a product of two trigonometric functions. For these cases, we often let you be the part whose derivative is simple and to be the part that is easy to integrate. So we'll set u equals sin of x and dv equals sin of x dx. Now we apply the formula. Substituting, we get sin of x times negative cos of x minus the integral of negative cos of x times cos of x dx. This simplifies to negative sin x cos x plus the integral of cos squared of x dx. We have a new integral cos squared of x. We can't solve this directly, but we can use the Pythagorean identity. Remember the identity. Cos squared of x equals 1 minus sin squared of x. Substituting this into our equation gives us negative sin x s x plus the integral of 1 minus sin squared of x d. We can split the integral into two parts. This gives us negative sin x cos x plus the integral of 1 dx, which is x, minus the integral of sin squared of x dx. And look, just like our last example, we have the original integral on the right side. We've got another recurring integral. Let's call the original integral I. Our equation is I equals negative sin x cos x plus x minus I. Add I to both sides to get 2I equals x minus sin x cos x. Divide by 2 and add the constant c. This gives us our answer. The memo then uses a half-angle identity, 2 sin x cos x equals sin 2x, to simplify the expression further. This gives us the final simplified answer. The memo confirms the result. Verified using memo. The key takeaway here is that integration by parts can be used to handle powers of trigonometric functions, which often leads to a recursive solution. Our next problem, example 4.36, is an excellent example of how there can be multiple ways to solve an integral, and it's always good to find the easiest way. We want to determine the integral of tangent cubed of x. The first method the problem presents is integration by parts. This method will work, but it's quite long. We split tangent cubed into tangent of x times tangent squared of x. Here we choose u equals tan of x and dv equals tan squared of x dx. Differentiating u is easy, but integrating dv gives us tan x, which is a bit messy. Applying the formula and simplifying leads to a complex expression that still contains another integral, x sec 2x dx. This requires us to use integration by parts again, just for that part. It's a solvable method, but it's clearly very cumbersome. Let's now look at the alternative solution provided, which is much shorter and more elegant. The alternative solution starts the same way, by splitting tangent cubed into tangent times tangent squared. However, instead of using integration by parts, it uses a trig identity. It uses the identity that tangent squared of x equals secant squared of x minus 1. This is a clever and powerful move. Substituting the identity, we get the integral of tan x times sec 2x1 dx. Now we distribute tan x to split this into two separate integrals. The integral of tan x sec 2x dx minus the integral of tan x dx. Both of these integrals are now standard and easy to solve. For the first integral, notice that cc2x is the derivative of tan x. So we can use the power rule for functions from our first slide. This integrates to 1/2 tan squared of x. The integral of tangent of x is, as we've seen before, the natural logarithm of the absolute value of secant of x. Combining our two results gives us the final answer. 1/2 tan squared of x minus the natural log of the absolute value of secant of x plus c. This is the exact same answer as the long integration by parts method. The important lesson from this example is to always think creatively. Trig identities can be powerful tools that sometimes make an integral much easier than a more direct application of a complex technique like integration by parts. Let's tackle another recurring integral. In this scene, our objective is to find the integral of secant cubed of x. We need to find the integral of secant cubed of x dx. First, we split secant cubed of x into secant of x times secant squared of x. For this specific integral, a standard choice is to let u be secant of x and dv be secant squared of x. Differentiating u gives do equals secant of x tangent of x dx. Integrating dv gives v equals tangent of x. Now we apply our formula. We get secant of x tangent of x minus the integral of secant of x tangent squared of x dx. Let's rewrite tangent squared of x using the Pythagorean identity sec 2. 1. This gives us secant of x tangent of x minus the integral of secant cubed of x minus secant of x. Splitting the new integral, we get sec x tan x minus the integral of secant cubed of x plus the integral of secant of x. And once again, we see the original integral appear on the right side. This is the recursive pattern we're looking for. Let's call the original integral I. Our equation is I equals sec tan x minus I plus the integral of sec x. We add I to both sides to get 2I. The integral of secant of x is a standard integral. It's the natural logarithm of the absolute value of sec x plus tan x. So 2I equals our expression plus the natural log term. Finally, we divide by 2 and add the constant c. This is our final answer. The memo confirms our result. Verified using memo. This is a classic and very important example of a recursive integral. Knowing how to solve sec3x dx is a valuable skill in calculus. We've reached our final example, which is another special case. Our objective is to learn how to integrate exponential functions that are multiplied by a sum of functions. We need to find the integral of e to the power of x times the quantity tan sec x plus sx squared x dx. This one looks complicated, but it has a very elegant solution if you recognize the pattern. The pattern to look for is the integral of e to the x times a function f, of x plus its derivative f prime of x. This pattern has a simple result. The integral is just e to the x times the original function plus c. Let's see if our example fits this pattern. If we let f of x be tan of x, what is its derivative, f prime of x? It's secant squared of x. So our integral is indeed in the form of e to the x times the function tan a plus its derivative secant squared of x. It's a perfect match. Therefore, the solution is immediately e to the x times tan of x, plus our constant of integration. See, that's a much faster way to solve it than the integration by parts method suggested by the textbook. But just to prove this works, let's quickly show how the integration by parts method would lead to this same result. The textbook says to apply integration by parts to just the first integral. We split the original integral into two parts. The integral of e to the x tan of x dx plus the integral of e to the x sec squared of x. For the first integral, we'll use integration by parts. According to ILATE, we let u equal tan of x and dv equal e to the x. Applying the formula gives us e to the x tan of x minus the integral of e to the x sec squared of x dx. Now let's substitute this back into our original equation. Notice what happens here. We have a negative integral of e to the x sec squared of x dx and a positive integral of the exact same term. They cancel out. The two integrals sum to 0, leaving us with just e to the x tan of x. We add the constant of integration, c, to get our final answer. It's the same answer we found instantly by recognizing the pattern. The memo confirms our result, verified using memo. Let's work through one more comprehensive example, example 439, that wasn't included in the main list of problems but is provided in the document. We need to determine the integral of cos of the natural logarithm of x. This problem is a combination of two things we've learned. It doesn't look like a product, so we'll treat it as 1 by multiplying by 1, and it's also a recurring integral. We'll rewrite it as the integral of 1 times cos of ln x dx. For this type of problem, where we have a trig function of a logarithmic argument, it's a good strategy to choose the trig part as u. We set u equals cos of ln x and dv equals 1 det. Now we apply the formula. We get x cos of ln x plus the integral of sin of ln x dx. Note that the x from v and the 1 over x from do cancel out, simplifying the new integral. We have a new integral, the integral of sin of ln x dx, which is similar to our original integral. This means we're in a recursive situation and need to apply integration by parts again. We apply integration by parts to the new integral. To maintain consistency, we'll again choose the trigonometric part as u, so u equals sin of ln x and d equals 1 dx. Now we substitute these into the formula for the second time. This gives us x sin of ln x minus the integral of cos of ln x dx. Let's substitute this entire expression back into our main equation. And there it is. The original integral appears on the right side. Let's call our original integral I. We have I equals x cos of ln x plus x sin of ln x minus I. Adding I to both sides gives 2I equals x cos of ln x plus x sin of ln x. Finally, we divide by 2, add the constant c, and factor out x over 2. This gives us our final answer. The memo confirms our result, verified using memo. Let's quickly review what we've accomplished in this tutorial. We started by deriving the integration by parts formula from the product rule of differentiation, which gave us the powerful tool. The integral of u dv equals uv minus the integral of v du. We learned how to choose the u and dv parts using the ILATE mnemonic, which helps us simplify the integral on the right side. We also saw some special cases, integrating single functions by multiplying by 1, solving recursive integrals by setting up an equation, and recognizing integrals that cancel out beautifully. And most importantly, we learned to always look for the simplest method first. Integration by parts is a cornerstone of calculus. It allows you to tackle a vast array of integrals that would be impossible with simpler techniques. Keep practicing, and you'll master this essential tool. Thank you for watching this tutorial from Math Zone African Motives. If you found this video helpful, please subscribe to our channel for more math tutorials. See you in the next video.